Welcome class to our presentation. Today we'll be covering our project, which is the Gearbox design. Our team members are Alonso, Aranega, and myself, Vila. For our problem statement, we had to design a gearbox that would reduce the speed and rotation. The speed had to be reduced from 2800 RPMs to 180 RPMs, and the rotation had to be, the input had to be clockwise as well as the output. Now, one of the constraints was that the input versus the output had to be perpendicular to each other. The other thing was that we had to transmit 6 horsepower with moderate shock throughout the whole assembly, as well as properly select the gears from a catalog that is being used in the industry and test the gears for stresses and the strains using the ACMA failure equations throughout the whole design. Now for the design concept, here's our final design iteration. We selected the gears from the Boston design catalog, and here we can see for gear reductions, and at the end we can see a bevel gear in order to make the input perpendicular to the output.
So based on the design constraints and parameters, we use the Boston gear catalog to select our gears based on the calculations done, which will be shown in the next slides. Using the Boston gear catalogs, we used these gears shown here by this Boston gear catalog number, and we have a total of 10 gears. Each gears are paired off, and we have the first gear with like 16 teeth, and then it goes on from there. The materials for all these gears are steel, so they can sustain more shock and more torque on them. To show how we got these numbers and how we were able to test them out, we used the Boston gear catalog to try different gear ratios and different gears with different number of teeth to see if they can withstand the horsepower that needs to be transmitted into the system. We were given the initial parameter of transmitting 6 horsepower at moderate shock. What that translates to is the system may peak at slightly above that 6 horsepower, which in this case for moderate shock would be about 7.5 horsepower, which you can see right here for each of these tables. Okay, and since we plugged in various gears, it was trial and error at first. Once we started seeing that the numbers were being able to sustain that horsepower, that's how we selected the gears, essentially. Here you can see, for example, this first table here shows the analysis for the first input gear, which is then mated to this gear on the bottom here, which, as you can see, it's a 16-tooth gear mated with a 32-teeth gear, which would give a theoretical gear ratio of 2:1. So for every 2 revolutions of the input gear, we have 1 revolution of the output gear. Since we have 4 stages, the overall gear ratio of this transmission or this gear train would be 16:1. As you can see, as the speed reduces, as the amount of revolutions reduces from gear stage to gear stage, it can be seen that the torque being applied is increasing as the gears increase in stages. So that's one of the main issues that we were having, was that some of the gears in the Boston gear catalog weren't able to withstand that amount of torque, and it would be prone to failure at the end. Using this, we then were able to figure out the gear contact stresses and the safety factors, as well as the gear bending stresses and safety factors for each gear, to see if they will be able to withstand those loads. As you can see here, most of this, all of the safety factors are above 1.3, which is the standard for these gears, and therefore it would mean that this gear system would be able to handle these stresses. Since we also had to make the input shaft and output shaft perpendicular to each other, we also had to include a bevel gear, which can be seen here. And very similar to the previous slide, we had to do some trial and error to figure out what would be the best option. And we were given, based off our calculations, a bevel gear with 25 teeth was the best option to be able to transmit that load. And now to Mario with the applications.
Some real-world implementations of this application would be such thing as a trenching machine. This is anything that needs a high horsepower, low RPM system. If it needs to cut through tough terrain or materials, this is definitely the way to go, and you can see it in industry and commercial and residential uses. To conclude, our design would be a low maintenance design simply because it would be fully immersed in oil, and such systems can outlive the life of the machine that it is used for. And we also learned a few lessons throughout the design process, simply because the first few iterations were failures, and that only made the final outcome that much better. And overall, we could say that we met our design constraint.